Now I'm going to start with segmentation. I have deliberately written this word segmentation using different colors. You can see that this segmentation word is one word made out of different alphabets. You can differentiate between alphabets using different ways. For example, you can segment out this S from E using, for example, color, corners, or you're learning because you already know, somehow your brain knows that this is an S and this is an E. So just to separate out S and E, there are different ways, and in the same way you can segment out all the alphabets present in this word segmentation. So what is segmentation? Segmentation is a grouping process in which the components of a group are similar with respect to some feature or set of features. You are going to, for example, in your class, I am segmenting out the students, and the feature which I am going to use is the gender. So using a gender, I can segment out your class very easily. I can I can ask all the males to go at one side and all the females to the other side. So this is one way of segmenting different portions of your class. The other feature which I can use is, for example, I can use height. I can say that every student, all the students who are taller than 5'9", for example, they stand on the one side and all the other should stand on the other side. Now I'll have two groups, and what will be the similarity in the students belonging to one particular group? The similarity over here would be that all the students present in that group, they have height less than 5'9", or for example, if I choose the other group, height greater than 5'9". So there is some common feature in all the students present in some particular group. So this is segmentation, that you are dividing things based on some particular feature. So once you have done segmentation, all the objects belonging to a particular group, they will have some common feature in them. As I have given you two examples of segmentation, so it can be easily established that segmentation is quite context dependent idea. You can, depending on the application that what you are going to do, segmentation can vary. Just like I have divided your class using gender feature and then using height feature, I can uh, have many other different features depending on the application that what I wanted to do with the class. So it is dependent on the context in which I'm performing segmentation. However, a range of problems can be solved without having any higher level knowledge. For example, right now you are segmenting the background, the white background of this video from the text present on it. So you don't need any higher level knowledge that what is the purpose of this text, what is written over here, why do you want it, what do you want to do with it. You don't need to know anything about it, but still you can segment out the text from this white background. So there are basically three main categories into which segmentation methods can be divided, and I'm going to go through these three main categories in the later lecture. The first one is global knowledge-based techniques. We are going to study that what are these things. The second one are based on edges. So we will find some edges and we will try to segment out objects using the edges. And these edge-based techniques, they are augmented using another category of segmentation techniques, which is called region-based techniques. So there are certain techniques where we have regions that keep on growing until they find a different object. So the idea in region-based technique is like that. For example, you have an image like this, and there are different objects present, but obviously you don't know that where are the objects and what is the size and shape of the objects. So what we do, we start from a random point. For example, we can start from here, for example. We'll keep on growing, we will keep on growing in all directions unless we meet a boundary or an edge. So you can see that when it will meet over here, this is going to happen, and it will keep on growing, it will keep on growing unless it has covered this whole object. Now there is no more room for growing. So this will be the output of the region growing. There won't be any holes over here. I cannot draw very exactly. It will be completely filled. So this will be the answer of region filling. So this is a region-based segmentation technique. Obviously, you are going to start from multiple points, not from one point, because if you start from one point, you are going to find only one object. But if you start from multiple points, you are going to find multiple objects. Okay, so now I'm going to start with global knowledge based segmentation techniques. And okay, so all these three main categories, they can either produce complete segmentation or they can produce partial segmentations as well. Complete segmentations are normally produced by region-based segmentation techniques or global knowledge-based segmentation techniques. Edge-based segmentation techniques, they can never produce complete segmentation. By complete segmentation, I mean that no further steps are required to segment out the objects. Whereas partial segmentation technique means that you need to apply some more steps on it, some more operations on it to find a completely segmented object. So normally edge-based segmentation techniques, they will produce some partial segmentations, and then region-based segmentation or region filling operations, they will be performed on the partial segmentation to get a full segmentation. And also, it is not necessary that global knowledge-based techniques and region-based techniques, they produce complete segmentation. They will produce complete segmentation for very simplified images. For example, the image which you are currently seeing in this video slide, you can easily segment out this image completely using, for example, thresholding. But if you use a real life image, then a complete segmentation will not be possible in a single go. So you will produce some partial segmentation, and then you have to perform some other operations on it to get a complete segmentation. Okay. So the global knowledge based techniques, they are quite common and quite easy as well. So the first one is the easiest one, which is called thresholding. You have already studied it, that what thresholding is. You must already know it. So it is the simplest segmentation process. And using thresholding on brightness images is quite a common thing for segmentation. So if an object has a constant brightness, then you can easily use a certain brightness threshold to mark that object as, for example, white and everything else as black. So you can easily segment out things using simple thresholding. So it is computationally inexpensive and quite fast. So that's why it is used quite commonly. So as I've already said that complete segmentation can result from thresholding, but in quite simple scenes. But for complex scenes, complete segmentation is not going to happen. If I formally put thresholding over here, then it is that for all the pixels Fij, having a threshold value greater than t, you will assign them 1, and all the pixels having a brightness value less than a threshold t, you will assign them a 0. So you are going to get a binary image as output, which will have 1 in place of, for example, an object, and zeros everywhere else. So this is the simplest technique, segmentation technique, and we have already used it. As you make the things simple, there are certain limitations associated with it. So over here, you can easily see that using only gray levels or a fixed gray level to segment out object is not such a great idea, because in real images there is no object which has a constant brightness value. The brightness values or the gray level values of the objects, they fairly vary. And another problem is that objects should be not touching each other. If they are touching each other, then this segmentation technique will label both the object as a single object. For example, if there is an object like this is one object, when one very simple object, and the other object is over here, and the third one is touching it a bit. So what you are going to get after thresholding, you are going to get only two objects. It will label this object as one object and this object as another object. So this is the problem with this segmentation technique. It is going to label both of these objects as one object because they are touching, they are connected with each other. Okay, so that's the problem with it. So here are some results of using different threshold values on this grayscale image. On this one, this is a grayscale image. You can use different thresholding values and you can see that the results varies as we change the threshold values. No matter what, gray levels are going to vary along the image, which will make a single thresholding value unsuitable for the whole image. So what is the remedy? The remedy is adaptive thresholding. What if we can have a new threshold value, a change threshold value for a different portion of the image, depending on the brightness values present over there and depending on the things over on in that locality. So hence adaptive thresholding, it will select a threshold value using some information present in a particular location of the image. So formally put, you will have this thing. The threshold value, this threshold value, it is not dependent on the image only, but it is dependent on the location where you are performing thresholding. If you remember this function that uses Utsu's method for finding an optimal threshold value, this Utsu's method will give you a threshold value for a particular image, but this method is going to use a complete image for once. But what if you need different threshold values for different locations of the same image? Then you'll have to provide this method with different windowed versions. For example, this one is a complete image and you have divided this image into 4 portions. Sorry, let me remove it. Okay, so you have divided this thing into 4 portions, 1, 2, 3, and 4. Now in the first step, you are going to provide portion number 1. You are going to get one threshold. You are going to use that threshold over here. You know that you cannot use this threshold over here. So now you can provide this Utsu's method with portion number 2. you are going to get a certain other threshold value. You can use that threshold value over here, a new threshold value over here, and a newer threshold value over here. So for every location, you are going to use a different threshold value. So this is adaptive thresholding. Okay. So now I'm going to move towards another thresholding technique, which is called a band thresholding. So you can modify basic thresholding technique in different ways, which we are going to see. What this band thresholding does, it will threshold a certain band of gray levels only, and it will remove all other gray levels. So it is quite similar to simple thresholding. So mathematically what it is doing, it is assigning this one to all the pixels belonging to some set of gray levels. For example, I can say that all the gray levels between somewhere from 100 to, for example, 160, all the gray levels between 100 to 160, they will be assigned 1 or the white value, and all the other gray levels, they will be assigned 0. The use of this thing can be established from two examples which I'm going to quote. The first one is, for example, in the inspection of uh, blood cell segmentation, a particular gray level interval represents cytoplasm. It has a background which is lighter and the cell kernel is darker. So a cell looks like something like this. So there are cytoplasm in it. For example, my drawing is quite poor and I don't know that how exactly cytoplasm looks like. But this region, this bordering region, it is quite darker. So it is darker. This region is quite lighter, and the cytoplasm has some intermediate value. So the band thresholding can be used to extract these cytoplasms very easily. Okay, if we threshold the gray levels associated with this intermediate range and assign everything else with a black color, what we are going to get? We are going to get this thing. There will be black portion everywhere else, and the cytoplasm, they will be white. So we are not concerned whether where is the boundary, where is the background, where are some other things present in this cell. Now we only know that where is the cytoplasm. Okay, so you get the idea. And another example is of border detection. If you have placed some dark object onto, for example, a light background, then some pixels will be present in the borders which have a little less darker values than the object and a little darker values than the background. So if you can find that interval, you can easily detect the borders. For example, in this image, these pixel values, they have some special gray values. So there exist certain pixels which are present over here like this. These pixels will have values different than the object and the background. So if you can figure out this interval, then you can apply band thresholding and get this kind of boundary detection. It is recommended to use this kind of band thresholding on very simplified images. On real images, you cannot, believe me, that you cannot detect boundaries like this. Okay.
So some more modifications to simple thresholding techniques. We can have this kind of band thresholding as well, where there is not one band, but there are multiple bands. So you must have seen some things like an MRI scan or a CT scan. There you normally have, for example, five or six colors, or five or six gray levels, you can say. So what is happening? So instead of dividing the whole image into a white and a black area, that is the binary image, you are defining or you are assigning one gray level to a particular object, another gray level to some other object, another gray level to some other object. You can have all the objects labeled with different gray level. If we can draw the graph for this grayscale transformation graph for this kind of thresholding, then it will look like something this. So this is the input gray level. They will vary from 0 to 255, obviously. There is the 0. This will be the output gray level. And what you're going to have, you will have, for example, this gray level for all the pixels from 0 to, for example, D1. And you can have, for example, this gray level for all the pixels between D1 and D2. And you will have, for example, this gray level for all the pixels between D2 and D3. And for example, you can have this thing. For all the pixels between D3 and 255, they will be assigned this gray level. So you are using four gray levels. For example, this is G1, this is gray level 2, this is gray level 3, and this is gray level 4. So now your image is not a binary image, but it has four gray levels in it. And all these four gray levels are representing four different regions. So you have segmented out your image into four different regions. Okay, so this is a modification of band threshold and where you use multiple bands. So another modification is called semi-thresholding. And what is this thing? You are not assigning one or some other gray level to the pixels having gray values greater than certain threshold. But what you are doing, you are assigning the input gray level to all the pixels having gray level greater than t, and all the other pixels you are assigning to them 0. So what is going to happen? For example, this is a colored image and you want to apply semi-thresholding to it. This is the result. For example, this one is the grayscaled version of the original image. How you can achieve this thing? You can see that over here everything is black, but the coins are in their original gray levels. So what you have done, you have semi-thresholded this image. You have not lost the gray levels of these coins, but you have deleted all the gray levels present in this background. If you have applied simple thresholding, you would have got this thing. So you can see that everywhere there is a coin, you have a white color, and everywhere else you have a black color. If you simply multiply this with the original image, this one, you are multiplying these two images, what you are going to get? You are going to get this one. So you have not lost the colors of the coins over here. Over here, the gray levels were preserved, but over here, colors are preserved as well. If you have, for example, a colored image. So for human analysis, over here, you cannot identify that what coin is this. You know that it is a coin. You know that it is some other coin. You know that it is some other coin, but what coin exactly it is? But over here, you can readily identify that what coins are these. So now there is no background, only coins are there. You can easily see the business over there. So you don't need to look anywhere in the background, or you don't need to be worried about that what is happening in the background and what information is present over there or not. So as I've stated this thing at the start of the lecture or this session, that thresholding doesn't necessarily depend on gray level image properties. You can use any property to threshold an image. You can use, for example, gradients. You can use some other texture properties. You can use anything that is present in the image to threshold the object. For example, for example, you can, if you have this kind of image, you can use corners to segment out the object. You know that over here you are not going to get any corners, but over here you are going to get some corners. So all the objects that don't have any corners in them, they are put into one category, whereas objects having some corners or a particular number of corners, they will be put into the other category. So over here, we are using the corners. We are not using brightness values. We are not using anything else, but what we are using the number of corners present in the object. So you can use any property of the object or anything, any information present in the image to segment out different objects present in that image.